And meanwhile, I'm sharing a link to the slides, if you don't mind. So I'm sharing in the chat the Dropbox link. Very good, it works. Okay, so I'm pleased to introduce Dmitry Timashev from Moscow State University. He will talk about real orbits in spherical homogeneous spaces.
Yeah, so thank you, Dima, for the introduction and for the invitation to this seminar. I hope that everyone hears me and sees my slides. If not, please tell me. Let me start for warming up. Let me start just with an undergraduate linear algebra problem of classifying quadratic forms over complex numbers and real numbers. For simplicity, I will consider non-degenerate quadratic forms, but actually this doesn't matter essentially. As everyone knows, at least those who passed an exam in linear algebra should know that over complex numbers, there is a single equivalence class of non-degenerate quadratic forms given by this representative. And over real numbers, the situation is a bit more complicated. There are several equivalence classes distinguished by inertia of quadratic forms. And actually, this is a manifestation of a general phenomenon. When you try to classify some objects in algebra or geometry of some type, like quadratic forms or, for instance, Lie algebras of given finite dimension, which are given by their structure tensors, or like configurations of several subspaces in a vector space or whatever, the objects which are defined over some base field. It often happens that the number of equivalence classes for these objects over a given field is bigger than over its algebraic closure. This is a very general phenomenon. And yet another observation is that equivalence of objects in such kind of classification problems is often given by an action of an algebraic group, so that equivalence classes are nothing but orbits for this action. So what is a proper way to formulate this kind of problems, this kind of classification problems in general? The general setup is as follows. Let X be a given algebraic homogeneous space defined over some base field K, so that G is a linear algebraic group defined over K. H is the stabilizer of a base point, a chosen base point on this homogeneous space. And both G, X, and the action of G on X are defined over this base field. This essentially means that the formulae, the equations, the formulae defining these actions, these things have coefficients in this base field. Then, since X is assumed to be homogeneous, the group of points of G over the algebraic closure of K acts on the K bar locus, the locus of K bar points of X transitively. There is a single orbit. But in general, the group of K points may act on the locus, on the set of K points of X with several orbits, and even it may be infinitely many orbits if, well, it depends, of course, of the field, of the base field. So the problem, yeah?
Do you assume anything about the characteristic?
So far not, but later on I will impose restrictions on my base field. The natural problem to which many classification problems reduce is to classify the orbits of this K point of K points of G acting on K points of X. And what we are doing, this is a joint project with Stephanie Cupit-Foutou from Bochum. We handle this problem under certain restrictions. So the first natural restriction is, of course, that K points should exist. Otherwise, there is nothing to classify. And if so, then you may assume that you may choose the base point of your homogeneous space for convenience to be a K point. so that the stabilizer is also defined over K. And conversely, if you have a group, an algebraic group G defined over K and a subgroup defined over K, then you may consider the homogeneous space G mod H, and it comes equipped with a natural K structure. It is also defined, it gets defined over K also. So the second restriction is that G is assumed to be reductive, connected and reductive, and X is assumed to be a spherical homogeneous space. I guess that at this seminar, maybe most of you know what is a spherical homogeneous space, spherical variety, but let me just, for the sake of clearness, because sometimes the definitions are slightly different, let me just emphasize that by a spherical homogeneous space, I assume a homogeneous space under a reductive group such that any Borel subgroup in G has an open orbit on the space. So X is assumed to be spherical. And so far, we deal only with the case of the field of real numbers. So the base field is assumed to be real numbers. This is, of course, a very strong restriction, but I mean, at least for applications, it is interesting, and as the first stage, it is quite natural to start with real numbers. Well, for the reasons which will be clear later on. Okay, so so far under this setup, we have done two cases. The first one is the case of a symmetric space. That is, the stabilizer is assumed to be up to connected components. It is assumed to be a fixed point subgroup of some involution on G. Symmetric spaces are always spherical, so this case fits in the general setup. And the second case, which we consider, is the case of split group. We assume that G is split. So in these two different cases, we get an answer which we consider as satisfactory for this general classification problem. Let me say that the example which I started with, the example of quadratic forms, fits in both cases. So in this case, X is a variety of non-degenerate quadratic forms in n variables. And it is acted on by GLN with its natural split structure. And if you choose for the base point one of the canonical normal forms, normal shapes of a quadratic form over real numbers, which you have seen on the first slide, then the stabilizer will be a pseudo-orthogonal group. And it is a symmetric subgroup of GLN, namely the fixed point subgroup of an involution theta given by this formula which you see. So it is essentially theta of G is the inverse transpose of G with respect to the quadratic form stabilized by H. So as I said, the symmetric, each symmetric space is always spherical, but in this example, you can see it just by hands. If you take for a Borel subgroup the standard one of triangular matrices, then the open D orbit in the space of quadratic forms is given by non-vanishing of upper left corner minors of the matrix of this quadratic form. Okay, so the main theorem, which I can formulate now only vaguely, later on the formulation will be specified, reads as follows. So under certain conditions on my spherical homogeneous space, we claim that the set of real orbits on the real locus of X is in a one-to-one correspondence with another orbit set. The set of orbits for some finite group Wx on the orbit set of some subvariety, well, of the real locus of some subvariety Z, modulo the action of the real locus of some torus in G, which I denote by T. So let me comment on the notation. Here, T is a maximal split torus, which should not be mixed up with the split maximal torus. The latter doesn't exist unless G is split itself. So T is a maximal split torus in G. Z is a certain orbit of T in X, which will be called a slice. And I will specify what is a slice later on. Wx is a certain subgroup in the Weyl group of T, which is called the little Weyl group of the homogeneous space X. And it is a finite reflection group which preserves the character lattice of Z. So Z is a T orbit, and also Z carries, Z is also a torus, so it has a character lattice. And this character lattice is preserved under this subgroup, the little Weyl group. And of course, since Wx preserves the character lattice of Z, it acts on Z, and this action normalizes its natural action on T. So there is a natural action of Wx on these guys, on Z of R, T of R, and on the quotient set. But the action which is considered in the theorem is not this obvious one. It is fancy. It is obtained from the obvious action by some twist. So it still normalizes the T action, but it is not straightforward to define. So this is how the main result looks like. And let me say why it is useful, why we find it useful. The point is that the orbit set of this, so the first point is that the orbit set of TR, of real T, or in real Z, is easy to describe. So if you are given a T orbit, given explicitly by its character lattice, and if you want to consider its real points and the action of the real part of T on these points, then the orbits are very easy to describe in terms of these two lattices, the character lattice of T and the character lattice of Z. So I won't elaborate on this much because it is indeed easy. And the second point is that this little Weyl group is also well understood in the theory of spherical varieties. We know what are its generators. We know we can, so we have an explicit embedding of this little Weyl group in the big Weyl group. So it is clear how to handle this group. That's why this theorem gives at least some approach to describe explicitly the real G orbits on the real locus of X. So to solve this classification problem in the special setting which we consider. Okay. As I said, we are able to prove this theorem in two different cases, and in these two different cases, we use different techniques. So, in the case of symmetric spaces, we use a very standard tool for study of such kind, for resolving of such kind of classification problems, which is Galway homology. Since I consider only only real numbers as the field of definition, let me briefly explain what is Galway homology over real numbers, because it is indeed very easy. So we have a map, a complex conjugation map on complex points of G and X, which I denote by bar. And the main feature of this complex conjugation is that a point is real if and only if it is complex conjugate to itself. So this is an involution acting on complex point of G or complex point of X, not regular, not holomorphic, but anti-holomorphic involution. But still, I mean, this is this map. This map has this feature that fixed points of this map are exactly real points. And also, since I assume that my action is defined over real numbers, the complex conjugation map is compatible with the action. This is expressed here. So we define, one defines the set of Galois cocycles of degree 1 over real numbers with coefficients in the acting group as the set of those elements in G of C which are inverse to their conjugates. These are Galois 1 cocycles. And on this set of 1 cocycles, there is an action of complex G by twisted conjugation. So it differs from the usual conjugation by taking bar here, by putting bar here. It is easy to see that the set of cocycles is preserved under this action. And the Galois cohomology, the Galois first cohomology set, is just the set of orbits for this action of complex G on 1 cocycles. Let me warn you that in general, it is not a group. So the cohomology, Galois cohomology is not a group. It is just a pointed set. You have the neutral element given by the unit element in G. This is the neutral element in the set of cocycles, and it gives you the neutral cohomology class. This is a base point. But there is no group law on this set, unless G is abelian. But still, since it is a pointed set, you may consider exact sequences. So the definition of an exact sequence is as usual. I mean, the kernel is what is mapped to the base point. And there is a nice exact sequence, including real points and Galois cohomology. So it is in 5 members. It contains 5 members. And all maps here are obvious, except maybe the last but one. For which I give a formula. If you have a real point in X, you may take you may obtain this point from the base point, which I also assume to be real, by applying some element of G. This G small needs not to be real, but since we get a real point, it is easy to check that this product G bar inverse times G actually is in the stabilizer of X naught. So this is an element of H, and this is a cocycle. It is easy to see that it is a cocycle. So its cohomology class sits in the first Galois cohomology of H. So this map sends the point X to this Galois cohomology class. And it's easy to prove. You can look in Serre's book for the proof, and also you can do it as an exercise, that the fibers of this map are exactly the orbits for the real locus of G acting on the real locus of X. Moreover, the cocycles which are obtained as the image of this map are those Galois cocycles of H which are coboundaries in G. Clearly, this cocycle is a coboundary in G, not in H, because G small sits in G, not in H. And therefore, we get the following statement, the following general statement, that the set of real G orbits on the real locus of X is identified, can be identified, it is in a bijective correspondence with the kernel of this Galois cohomology map. So this is maybe the main application, one of the main applications of Galois cohomology, at least in my opinion. This is very general. So you need not assume anything on G, on X, just that X is a homogeneous space defined over real numbers. But if you want to get from this general result an explicit description of orbits, then you need to have a good understanding of these Galois cohomology sets and of this map. So you need some Lie theoretic structure results on H, G, and the embedding of H in G. And this is not always available. Such Lie theoretic picture is not always available. It is indeed available in the symmetric case. So if H is a symmetric subgroup, then all these guys can be understood. And that's why in the symmetric case, which we started with, we used this approach first. So let me pass to the case of symmetric spaces. Recall that in this case, the stabilizer of the base point is a symmetric subgroup, that is a fixed point subgroup of some involutive automorphism of G up to connected components. So it follows from the structure theory of symmetric spaces, of complex symmetric spaces defined over real numbers, that you may choose a maximal split torus in G of some special form. It is a product of two subtori, T0 and T1, where T0 is a subtorus in H, that is theta acts on T0 identically. And T1 is a maximal split torus having an additional property, a maximal split torus on which theta acts as inversion. So you can choose a maximal split torus in the whole of G of this form. And let's consider now the group, which I denote by Nx. And let me call it the twisted normalizer of T1 in H. It is the set of elements in the usual normalizer, satisfying this additional condition that n times n bar inverse sits in T1. Why I call it the twisted normalizer? Because it is exactly the normalizer of T1 in H under the action by twisted conjugation. And this group, twisted normalizer of T1, acts on T1 intersect with H. And the letter set, it is easy to see that the letter set sits in the set. It consists of elements of order 2. And it sits in the 1 cocycles of T1 intersect with H, which in turn sits in 1 cocycles of H. So Nx acts on the smaller set of cocycles by twisted conjugation. And we prove, using some structure theory of symmetric spaces and the above general result about Galois homology, that actually the orbit set, which is identified with this kernel of Galois homology map, is naturally isomorphic to the orbit set of this T1 intersect with H by the twisted normalizer, by the twisted conjugation action of this twisted normalizer. So this is this result is already something, because for symmetrics, for particular symmetric spaces, this set can be described, but it is not of the form which I introduced in the main theorem. Let me transform this proposition into this form. So given any element in T1, yeah. Any question? No. Given any element in T1 intersect with H, I may I may take any element. Excuse me. Is it a question? No. Okay. So given any element in T1 intersect with H, we can choose an element in T1 satisfying this formula, this equality. And if you recall the correspondence between Galois cocycles and real points, then you see that to this element S, there corresponds a real point X obtained from the base point by applying this T. This is a point in the slice, because the slice here is the orbit of x0, the orbit of the base point. This is the real point in the slice. And the twisted conjugation action of this twisted normalizer on S amounts to replacing this element T with another element, which I write here. So you act on T by usual conjugation, and you make an additional shift by this torus element T of n, which is defined not uniquely. It is defined up to translation by a real element. But this element has to satisfy this equality. So if you replace S with another cocycle, then this point X will be replaced with another point, which is written here. So you basically apply the usual action of this twisted normalizer with an additional shift. And the general result on classification of real orbits via the Galois homology amounts to the following theorem in this case. So first, the action, this formula sending x to T of n and x defines an action of the twisted normalizer, not on the real points of Z, because, for instance, because this T of n is not uniquely defined. But it defines, it gives you a well-defined action on the set of real T orbits on the real locus of the slice. And this action actually factors through the action of the little Weyl group, which in this case is just the Weyl group of this torus T1. So the normalizer of T1 modulo its centralizer. This is the little Weyl group of a symmetric space. And consequently, we get that the set of real orbits for the set of orbits for the real locus of G acting on the real locus of X on my symmetric space is in bijection with the set of orbits for this little Weyl group on the orbit set of the real locus of Z acted on by the real locus of T. So we get indeed the result of the same shape as in the main theorem, which I announced. So this is the case of symmetric spaces. Actually, I don't want to elaborate much on this case for two reasons. So the first one is that this approach, this Galois homology approach, it is quite general, but to make it efficient, you need, as I explained, you need to have a good control over the Lie theoretic structure of the stabilizer, which we have in the symmetric case, and we don't have for general spherical spaces. As you know, maybe spherical subgroups in reductive groups, they are classified, but the classification is somewhat indirect. They are classified by certain combinatorial invariants called spherical systems, spherical data, and it takes some effort to extract a Lie theoretic description of a spherical subgroup from this data. And also this description is not uniform. Of course, in each case, you may obtain such a description by some effort, but there is no uniform picture. And the second reason is that, so this is why we need some different approach in the general spherical case. And the second reason is that actually this different approach, which we now pursue with Stephanie, it is interesting because it is linked with some other constructions in the geometry of spherical varieties, and we find it quite interesting and promising. So let me now turn to the second case, the case of split G. And let me explain what is our approach to classifying real orbits in this case. So let me first choose a Borel subgroup defined over real numbers and a split maximal torus in this Borel subgroup, denoted by B and T respectively. And if now if I consider my homogeneous space X, which I will identify freely with the set of its complex points, this I can do because of Hilbert's Neusteller-Satz. I denote by O max the open Borel orbit in this set, in this space. This set of real points, the real locus of X, is not a single orbit, as I already said. It is not a single orbit for the real locus of G, but there are finitely many orbits of G of R acting on X of R. And what can you say about these orbits? So you have a classical Hausdorff topology on X of R, and these orbits are open and closed in this Hausdorff topology. This doesn't mean that they are connected components, they are unions of connected components, but they are open and closed. And also they are Zariski dense, dense with respect to the Zariski topology on X. And since they are Zariski dense, each of them has a non-empty intersection with the open complex Borel orbit. So we may pick representatives of real G orbits sitting in the real locus of the complex open Borel orbit. So this is the first idea. If you look at this open Borel orbit, look at its real locus, then again it decomposes in a finite union of real Borel orbits. To solve our classification problem, it remains to answer two questions. The first question is how to parameterize the real Borel orbits in the real locus of the open complex Borel orbit. And the second question is which of them is to understand which of them sit in one and the same real G orbit, which of them glue together under the action of real G. So if you answer these two questions, then you get the classification which you search.
Excuse me, I guess I missed something. So yeah. X of R is a union of finitely many G of R orbits.
Yeah, exactly.
But some of them are G of R orbits.
G of R orbits. G of R orbits.
I see. Sorry. Yeah.
So it's okay. Yeah. Now it's clear. Okay. So let me try to explain how we answer these two questions in this case, in the split case. So the first question is actually easy to answer. The answer is based on the so-called local structure theorem, which goes back to Brion-Luna-Vust. Let me introduce some piece of notation. Let's denote by P the parabolic subgroup containing B, which preserves the maximal, the open Borel orbit, which preserves this O maximal. This is a parabolic subgroup, a standard parabolic subgroup containing my B, and it is also defined over real numbers. And we take its standard Levy decomposition, where P sub U is the unipotent radical of P, and L is the standard Levy subgroup containing T. There is a unique one in P. So it is also defined over real numbers. Everything is defined over real numbers. The local structure theorem of Brion-Luna-Vust, which was later on reproved differently by Knopp, says that the action of P on this open Borel orbit, O max, has a very simple structure. Actually, it is a homogeneous fiber bundle over P mod L. And so, thanks to this Levy decomposition, it decomposes as a direct product of PU and Z, where Z is the fiber of this bundle. Z is some subvariety of O max, some closed subvariety in this Borel orbit, which is stable under L. And moreover, the action of L on Z is transitive, and the derived subgroup of L acts trivially. So essentially, Z is a torus orbit. and this Z will be our slice. So the slice Z is the L orbit of the base point x naught, or equivalently the T orbit of this point, and it is a homogeneous space T over T intersect with H. H is the stabilizer of x naught. It is not absolutely clear from the proof of Brion-Luna-Vust, but if you look at Knopf's proof, then you can easily see that this slice can be chosen to be defined over real numbers. So again, everything in this theorem can be chosen to be defined over reals. And if you take a look at real points of O max, then you again get the same kind of decomposition. It decomposes as a direct product of the real locus of the slice and the real locus of the unipotent radical of P. What does it mean? This means that when you act by PU of R on the slice, then the orbits are transversal to the slice. And these orbits cover the whole real locus of O max. So this is this decomposition. So in view of this decomposition, if you are interested in real Borel orbits sitting in this real locus, then you may cancel out the action of the unipotent radical, and it boils down to real torus orbits on the real locus of the slice. So as a corollary of the local structure theorem, we get the answer to the first question, which I posed on the previous slide, that is the set of real Borel orbits in the real locus of the big complex Borel orbit of the open one is in a one-to-one correspondence with the set of real torus orbits on the real locus of the slice. Actually, each real Borel orbit intersects the real locus of the slice in a real torus orbit. This is how this bijection looks like. So the first question is answered. And let me emphasize again that this torus orbit set is very easy to describe. Maybe it's now a good time to illustrate this result by the example which I use throughout my talk as the illustrative example, the example of quadratic forms. In which case, let me remind that X is the set of non-degenerate quadratic, the variety of non-degenerate quadratic forms in n variables. G is GLN, and the maximal, the open Borel orbit is defined by the inequalities, by non-vanishing of this delta case, where delta case are the upper left corner minors of the matrix of a quadratic form. In this case, the local structure theorem, the data involved in the local structure theorem are described as follows. The parabolic subgroup P coincides with the Borel subgroup. It is the upper triangular matrices. Its unipotent radical is unitriangular matrices, and the Levy coincides with the maximal torus. It is diagonal matrices, the standard maximal torus, split maximal torus in GLN. And what is now the slice? The slice is the variety of quadratic forms which are sums of squares of coordinates with coefficients, so which are put in a canonical shape. What does the local structure theorem claim? It claims that each quadratic form with non-vanishing upper corner minors can be moved to this shape, can be transformed to this shape by a unitriangular change of variables. This is nothing else than a Gram-Schmidt orthogonalization process, actually. Now let's consider the action of the torus on the slice. When you act by a torus, the coefficients of a quadratic form are divided by squares of diagonal entries of this torus. And if you, this is over complex numbers. And so you easily see that there is a single orbit indeed, because all these coefficients can be made equal to 1. But if you are acting, if you are working over real numbers, then there are more orbits, because under this action, the signs of coefficients are preserved. So the orbits, the real torus orbits on the real locus of the slice are parameterized by tuples, by n tuples of pluses and minuses. There are 2 to n orbits in the slice. And actually, in the general setting, for any spherical homogeneous space, it is more or less the same. So the orbits are parameterized. The orbits in the real locus of the slice can also be parameterized by some tuples of signs. Okay. Now we have to answer the second question: which of these real Borel orbits, which correspond bijectively to real torus orbits in the slice, which of them are glued together by the action of real G? This is a more interesting part of our work and of my talk, I hope. But before explaining this, well, let me first say how it is done in general words. So the tool for doing this is to introduce some operators, some transformations on the set of Borel orbits, which correspond to simple roots. So this will be a kind of reflections, simple reflections acting on Borel orbits. We want to introduce these reflection operators on real Borel orbits and to link them to the question which we are interested in. But first, to do this, let me first explain the situation over complex numbers. Because what we are doing, it is actually an adaptation to real numbers of a construction due to Knop, who defines the action of the Weyl group on the set of complex Borel orbits in a spherical homogeneous space, even in a bigger generality, but let me stick to spherical spaces. So let me start with the complex case and explain Knop's construction. For any simple root of G, let me consider a minimal parabolic, the minimal parabolic subgroup, the standard minimal parabolic subgroup over B, corresponding to this simple root. If you take any Borel orbit in X, so far everything is over complex numbers, you may act by this minimal parabolic. You may span this B orbit by a minimal parabolic, and you obtain a P alpha orbit, which of course is now not a single B orbit, but it is a union of several B orbits, including the initial B orbit O itself and maybe some other orbits. The first thing to understand is to see what is the configuration, the mutual position of these B orbits inside the P alpha orbit. To understand this, we consider, so we start with the action of B on this P alpha orbit, but instead we may consider the action of B cross the stabilizer of some point on the group P alpha itself, where B acts from the left by multiplication on the left, and P alpha X, the stabilizer, acts on the right. And the orbit sets for these two actions are in a natural bijection, and also the Hasse ordering and the codimensions, for instance, for these orbits are the same for these two actions. And again, we can pass from this action to another action, to the action of the stabilizer P alpha X on P alpha mod B on the complex projective line. And it is in this language in which we can easily understand the configuration of orbits. So there are several cases depending on the image of the stabilizer in the automorphism group of P1 in PGL2. The first cases denoted as P is in which this group, this image denoted as Qx, is the whole PGL2. In this case, of course, we have a single orbit. The second case, case U, is the case in which the group Qx is in between some Borel subgroup of PGL2 and its unipotent radical. Of course, everything is up to conjugation. In this case, we have two orbits on PGL2, a fixed point, the infinity point, and the affine line. So there are two orbits. And the other two cases, denoted by T and N, are related to orthogonal groups. So the case T corresponds to Qx equal to the projectivized SO11, PSO11, or PSO2. This doesn't matter because we are over complex numbers. This is a maximal torus, just a maximal torus in PGL2. In this case, we have three orbits, the open one and two closed orbits, which are fixed points. And in the case N, the group is a bit bigger. It is the normalizer of the maximal torus in PGL2, which is the whole PO11, the whole projectivized pseudo-orthogonal group, orthogonal group. Over complex number, this doesn't matter. In this case, the open orbit is the same, and these two fixed points are in one and the same, form a single orbit for Qx. And this is indicated by this dashed line on the picture. So the picture, so this circle, you may imagine this circle as a projective line, complex projective line, or if you like, as a Riemann sphere. So this is a picture of the Riemann sphere. Now Knop introduces the action of the simple reflection corresponding to the simple root alpha on these orbit sets, in each case separately. So the action is given by these pictures. In the U case, the two orbits are interchanged. In the T case, the two closed orbits are interchanged. And all other orbits are fixed by this reflection. What Knop proved in 1995 is that these reflection operators, the simple reflections acting on Borel orbits, actually define an action of the whole Weyl group of G on the set of Borel orbits. This means that basically that they satisfy Braid relations because they are involutive already by definition. The only thing to check is to check Braid relations. So this action will be denoted by an asterisk in my talk. This is what was done by Knop in the complex case. And what we are doing, we extend this construction of Knop over real numbers. So we want to define reflection operators acting on real Borel orbits. So basically, the picture is very similar. So we start with any Borel orbit, any real Borel orbit O, sitting in the real locus of X. We act on this orbit by the real part of the minimal parabolic corresponding to a given simple root. And again, it decomposes in finitely many real Borel orbits, including the initial one. And the set of these orbits is in a bijection to the set of orbits for the real locus of the stabilizer in P alpha on the real projective line. So we have to take real points of all objects which we consider. The configurations, the possible configurations of orbits, the picture for possible configurations of orbits is more rich than in the complex case. Basically, what happens, some of the complex cases split into real subcases. This happens for the cases T and N. The cases T and N split into three subcases each. And the subcases marked by 0 correspond to the situation where the image of the acting group in the automorphism group of the real projective line, which I denote by Rx, is a compact group. In this case, the action is transitive, and we have a single orbit. So the picture is exactly the same as in the case P here. Despite that now this circle denotes not a sphere but a circumference. Also, the cases, there are two other subcases marked by 1, by the index 1, which are similar to the, in which the picture is similar to the complex cases T and N. Let me again show this picture. So in the T1 case, we have 3 orbits, an open one and 2 closed orbits. And in the complex N case, we have 2 orbits, an open one and a closed one, and the closed one. But there are 2 other subcases, T2 and N2, in which there are more orbits. So in the T2 case, we have 4 orbits, 2 closed ones, and 2 open ones. So there are 2 open orbits. I mean, open in this classical Hausdorff topology, of course, not in Zariski topology. And in the N2 case, there are, again, 2 open orbits, but still a single closed orbit, as in the complex N case. So the reflection operators, which we introduce on the real Borel orbits, are defined similarly to Knopf's definition, with the only difference in these 2 cases, T2 and N2. In these 2 cases, we define the reflection operators as interchanging. We define them to interchange the 2 open orbits. And for closed orbits in the T2 case, the definition is still the same as Knopf's one over complex numbers. So we have defined the action of each simple reflection on the set of real Borel orbits in the real locus of my spherical homogeneous space. But let me warn you that unfortunately, or maybe fortunately, I don't know, these reflection operators do not always define the action of the Weyl group on the set of real Borel orbits. This means that in general, they do not satisfy braid relations of the Weyl group of G. There are counterexamples, and well, at the first stage we believed that this is true, but afterwards we found these counterexamples, and that's why our final, not final, but our result, which we have so far, is maybe not in a final form. Maybe if I have time, I will say something about how the final result may look like. But still, although we do not get, in general, we do not get the action of the Weyl group on the set of real Borel orbits, sometimes under further restrictions, we do get such an action. Either, well, maybe not on the whole set of real Borel orbits, but on some subset of the set which is sufficient for our purposes, for the classification purposes. Let me remind you that for the classification purpose, for the classification problem, we need only open real Borel orbits, sitting in the open complex Borel orbit. Okay, so let me now go further and explain in which case we still have such an action of the Weyl group on a smaller orbit set. So the first theorem we get is the action of the whole Weyl group on some subset of real Borel orbits. Let me explain what is this set. So you have the complex Borel orbit, the open one, O max, and you can apply the Weyl group, the Knopf's action of the Weyl group to this orbit. You get some set of complex Borel orbits of the form W star O max. Well, for those of you who are familiar more or less with the theory of spherical varieties, algebraic theory of spherical varieties, it is clear that these are nothing but the Borel orbits of maximal rank, whatever it means. So let's consider the Borel orbits of maximal rank, complex Borel orbits of maximal rank. Let's consider their real loci, and let's consider real Borel orbits sitting in this real loci. So under a certain sophisticated condition, which is marked by the dagger, you indeed get the action of the Weyl group on this smaller set of real Borel orbits of maximal rank, given by this by the reflection operators which I defined on the previous slide. The condition is indeed a bit tricky. It says that the case T2, the case T2 should never occur for real Borel orbits of maximal rank. So let me remind you again that the case T2 in this case, it is the case in which there are two open Borel orbits, two open real Borel orbits in the real minimal parabolic orbit. So these orbits marked by O and O prime. And the reflection operator as alpha interchanged them. And in this case, we have counterexamples. We have counterexamples to the statement of this theorem. So this Gnostic condition or some analog of this condition indeed should be imposed. Instead, for instance, you may consider, you may impose the condition that X is a symmetric space. For symmetric spaces, it doesn't matter whether this T2 subcase occurs or not, but I didn't include the symmetric case in this theorem because it is already covered by a different approach. So under this restrictive condition, we have the action of the Weyl group on real Borel orbits of maximal rank. Maybe it is worth to say a few words about the idea of the proof. To explain the idea of the proof, I need first to explain the complex situation, the situation of the complex numbers, namely how Friedrich Knopp related the W action on Borel orbits with the geometry of the cotangent bundle of X. So the relation is the following. Let's consider the moment map sending the cotangent bundle of X to the dual of the Lie algebra of G, and compose it with the quotient map, with the categorical quotient map by the adjoint action, by the co-adjoint action of G. The categorical quotient is isomorphic by the Chevalier theorem to the categorical quotient of T star, the dual of the Lie algebra of T, modulo the action of the Weyl group. And we take the Cartesian square of this form. There is a natural map from T star to this quotient, and this is the fiber product, denoted as T tilde star X. Sometimes it is called the polarized cotangent bundle. And on this polarized cotangent bundle, we have a natural action of the Weyl group coming from below, from the action of the Weyl group on T star. Now let us take any B orbit of maximal rank, which is exactly a complex B orbit obtained from the maximal one, from the open one, by a sequence of reflection operators, by the action of the Weyl group, by Knopp's action of the Weyl group. And consider its conormal bundle. Not its conormal bundle, consider the conormal bundle of the foliation of orbits for the unipotent radical of B in this B orbit OC. So this is not a conormal bundle to a single orbit. It's a conormal bundle to a foliation. Let me denote it by this U over OC. And this conormal bundle can be canonically lifted to the polarization of the cotangent bundle. I won't explain how. It is in Knopp's paper. What Knopp proves is that the irreducible components of the polarized cotangent bundle, which are transitively permuted by the Weyl group, are actually the closures of G spans of these conormal bundles lifted to the polarization. And not only, so we get, by means of this, we get a bijection between Borel orbits of maximal rank and irreducible components of the polarized cotangent bundle. And not only we get this bijection, another statement proved by Knopp is that the action of each simple reflection on such an irreducible component sends it to another one, which corresponds to another B orbit of maximal rank obtained from the initial one by applying these reflection operators. This means that the reflection operators acting on B orbits of maximal rank match with the actions of simple reflections on the components of the polarized cotangent bundle. And since the latter action is indeed the action or is indeed an action of the Weyl group, we get the braid relations which we want to prove. So this is what Knopp did over complex numbers, and what we do here, I have to skip details because of lack of time. What we do is just an extension of this construction over real numbers. So basically, we consider real loci of everything here, and we prove a similar bijection. But now we are considering not irreducible components, but some open and closed subsets in the polarized cotangent bundle instead. They are neither connected nor the whole irreducible components, something in between. So, but still we have under this dagger condition, still we have such kind of bijection, and this proves the action of the Weyl group in the real setting. Let me come back. Another theorem which was proved by Knopp in the same paper is the description of the stabilizer of the open B orbit. This stabilizer is a semi-direct product of the Weyl group of the Levy, denoted as WL, and the little Weyl group of X. I haven't defined it so far, but you may look at this little Weyl group here just as a complementary subgroup of this guy in the whole stabilizer. And if you observe that the simple reflections corresponding to simple roots of the Levy, the simple reflections sitting in the Weyl group of the Levy, act trivially on real Borel orbits, on open real Borel orbits, on real Borel orbits sitting in the real locus of the open complex one. Because in this case we are, due to the local structure theorem, in this case we are always in the P case. Actually, we see that the action of this stabilizer, so this stabilizer preserves the complex orbit O max, and since the action is compatible by this theorem, this stabilizer acts on the set of open real Borel orbits. This stabilizer acts on this set. And this action actually boils down to the action of the little Weyl group on this. So we get an action of the little Weyl group under these conditions. Under this condition, we get an action of the little Weyl group on the set of open real Borel orbits. Of course, and sometimes under some different but simpler restrictions, we can define an action not of the whole little Weyl group, but of some subgroup in Wx on the same set, on the set of open real Borel orbits. This smaller subgroup, which we call a very little Weyl group, can be defined as follows. Let me again make some recalls from the theory of spherical varieties. There is a set of spherical roots in the character lattice of Z, of the slice, which is actually a base of a certain root system in this lattice. spherical roots is actually one of the data which are ubiquitous in the theory of spherical varieties, as in the geometry and classification. And actually, the little Weyl group is nothing but the Weyl group of the root system whose base is the set of spherical roots. As a subgroup of orthogonal transformations of the character lattice of Z, it is just generated by reflections along spherical roots. The smaller group, which we call the very little Weyl group, is generated by those by the reflections corresponding to those spherical roots, which are at the same time either simple roots of G or double simple roots, or they are doubles of double simple roots of G. So it is some smaller subset of spherical roots, and the reflections corresponding to them generate this subgroup WX hash, which sits in the little Weyl group of X, and both sit in the big Weyl group of G. Easy to observe that a simple root is spherical if and only if it is in the T case for the open Borel orbit, O max. So this relates this subset to the reflection operators which we introduced before. And similarly, a doubled simple root is a spherical root if and only if alpha is in the N case for O max. So the theorem which we have for this very little Weyl group is the following one. Suppose our homogeneous space satisfies an additional restriction, not additional restriction, but another restriction, double dagger. Namely, there do not exist two simple roots which are spherical roots at the same time, which have the same length and which are adjacent on the Dynkin diagram of G. If such a pair of simple roots does not exist, then the reflection operators corresponding to the simple roots which are spherical, or their doubles are spherical, define an action of the very little Weyl group on the set of open Borel orbits. Here, the idea of proof is quite straightforward. We make some reductions to the rank 2 case, and then we just check in the remaining cases, which are classified. We just check grade relations. Well, with some simplifications, but basically it is the proof is based on classification. So it is not as conceptual as the proof of theorem A. Now let me come to the conclusion. The problem which we faced in the classification of real G orbit is to understand which real open Borel orbits sit in one and the same real G orbit. Making use of the fact that the real loci of minimal parabolics generate the real locus of G as a group, we easily derive the following proposition. For any two open real Borel orbits, O and O prime, they sit in one and the same real G orbit, if and only if they are linked by a sequence of simple reflections corresponding to simple roots which are spherical or their doubles are spherical. It is more or less straightforward from this fact mentioned above about generation by minimal parabolics and the definition of reflection operators. And having this proposition, we get a corollary that under either of two conditions, dagger or double dagger, which I introduced before, for the respective groups, either the little Weyl group or the very little Weyl group, respectively, we have the following statement. The two orbits O and O prime sit in one and the same real G orbit, so they are glued together, if and only if they sit in one and the same orbit for this little or very little Weyl group. And finally, we get the conclusion which I formulated, which I announced in the main theorem. That is the set of real G orbits in the real locus of X is in a one-to-one correspondence. Well, first with the set of with the set of orbits for this little or very little Weyl group on the orbit set, on the set of open real Borel orbits, or as I explained before, with the set of orbits for this group, for this little or very little Weyl group, on the set of real torus orbits in the real locus of the slice. Finally, we proved, well, not proved, but we came to the end of the sketch for the proof of the main theorem. And let me finish now my talk with an example, with this illustrative example, which I use throughout. In this example, as I explained before, for quadratic forms, the slice is composed by quadratic forms which are sums of squares with certain coefficients. The maximal torus is just diagonal matrices. The set of real torus orbits on the slice is parameterized by tuples, by n tuples of signs, plus or minus. And on this set, there naturally acts the group, the symmetric group, the group of permutations of degree n, which in this case is both equal to the Weyl group, to the little Weyl group, and to the very little Weyl group, and also to the big Weyl group, of course. So here I can insert W also. In this case, all these groups coincide. And the action is natural. Of course, I do not explain how these two groups act on real Borel orbits or real torus orbits in details, but just trust me that the action is the natural one by permutations of these entries. So the orbits for this group are given by numbers of pluses and minuses, which are nothing but inertia indices of a quadratic form. So in this case, the main theorem specializes to the inertial law of Sylvester, as it should do, of course. Yeah, so maybe this is the point on which I can finish. I can stop, and let me show you the last slide on which you see some references. So the first paper, it is already published. It is about the symmetric case. And the second paper, so far it is not published, it is about the split case. So here in these two papers, you can find more details on what I have talked about. Thank you so much.
Any questions? Maybe I should say questions, please. Surely someone has a question.
Yeah, please, we have 15 minutes left.
Did I understand correctly that the very little Weyl group acts transitively on the maximal rank orbits in a given GR orbit?
No, yeah, in a given one, yes. In a given one, yes, but not on the whole set of maximal real Borel orbits. Actually, right. this is this claim that two orbits sit in one and the same real G orbit, if and only if they are in one and the same little Weyl group orbit.
Yeah, and do you also then get some kind of parametrization? I mean, so if you have, let's say, a point in the slice. In the slice in one open BR orbit in a given GR orbit, do you then get representatives of the other BR orbits
yes. Yes. Actually, it can be proved that you may just apply, you may just take a point, a representative in the slice, and apply a real element in the normalizer of T corresponding to this W. then you may go out of the slice, of course. It may happen that you go out of the slice. But it can be proved that you are still in the same Borel orbit, in the same B of R orbit. That means that you can get back to the slice by applying an element from the unipot radical of B of R. So it is an interesting question whether by means of this you get an action of this normalizer on the points of the slice. We do not know that. We have an action on orbits. We do not know whether we have an action on points. But maybe we do not have any counterexamples.
So there is also the paper by Knoop and I'm going to butcher his name. So the Vladimir Shgon.
Yeah, Vladimir Shgun. I'm not sure. Did they already publish anything together?
So they have a preprint at least together. So
in archive?
On the archive, yes,
okay.
I think so. Yeah. So and it seems very similar to what you are doing, but so I wonder what is the difference. So they get an action of the Weyl group on some quotient, but I think what is happening there is that I think they take somehow the minimal parabolic. So they don't look at split groups. But they have a minimal parabolic. I think they look at the orbits of the minimal parabolic, and then I think they get an action on those orbits, but maybe not on the let's say the R points. So the orbits of the R points of the minimal parabolic. So it seems that it's not exactly the same of what you are doing. It seems that what you have is more precise, but.
Yeah, I can comment on it. I know this work. I didn't know that it was already on archive, but I know this work. So what they do in the split case, what they do amounts to what Knoop did in 1995. Nothing new. What they do in the non-split case, they indeed consider since in the non-split case and even non-quasi-split case, maybe you do not have a Borel subgroup defined over real numbers. You replace it with a minimal parabolic subgroup defined over the base field, yeah, or the field of definition. And what they do, they consider orbits again of maximal rank, whatever it means. They consider orbits for this minimal parabolic subgroup which have k points, which have rational points. They consider these orbits and they define an action of some kind of little Weyl group, which can be defined similarly to what Knoop did. They consider the action of this little Weyl group on the set of this p orbit of this minimal parabolic orbits, not on the real loci, not on the orbits in the real loci, but on the k-bar orbits itself. But these k-bar orbits have to be defined over k. So this is indeed different from what we are doing. And actually, maybe it's a good time to show you another slide, what we can do next. So, by the way, we involve Shgun in this project. So far, we have no results, no further results, but we hope to get them. So, what we did, more or less did, is this upper node of this diamond, the case of split G and real numbers. What we can do next, we may consider indeed any G and still the case of the field of real numbers. And here indeed, we want to adapt the construction of Knoop and Shgun to our purpose. So we want to develop it further to get the action of some group related maybe to maybe not the little Weyl group itself, but some related group to on the real orbits. Not on the complex orbit defined over reals, but over real orbits. And indeed, we hope that the paper of Knoop and Shgun, the work of Knoop and Shgun, will help us. Another direction is to preserve the assumption of splitness, but replace real numbers with any k of characteristic 0. Here, of course, the Galois group should be more involved. it may be very complicated and should be involved in the picture. And if we will be lucky sometimes to elaborate these two nodes, then maybe finally we come to the general situation. But of course, this is just a desire. We have no concrete plans for this last stage. Yeah.
So for the assumption you have to make about this non-occurrence of the so this was the PSO1,1, I believe. So are you suggesting that you should change sort of the little Weyl group in that case, that you then maybe get some other group acting on it, or?
Yeah, indeed. What again we believe to hold true is that not the little Weyl group, but some extension of this little Weyl group should act on real Borel orbits, at least of maximal rank, at least those of maximal rank. And what this extension could be? Well, we believe that it should be an extension by an elementary abelian 2 group for some reasons. I don't have time to explain why, but somehow it is related to the nature of the Galois group because it is Z2. So it has somehow to be multiplied as many times as many simple roots we have, and to cook some extension. But so far we do not have a construction, a good general construction. In examples we can cook such a group, but only in examples.
So what would be an example here?
Let me. Should I try to show you a whiteboard? Let me try, because this is the way I'm teaching students now. So let me.
Oh, we get a blackboard?
No, not a blackboard, but a small whiteboard used by my kids, and I also use it for teaching. Let me show it. So just a moment. Yeah. Yeah, okay, I hope you see it. Let me, so how to make this the full screen picture? Who can tell me? Dima, do you know how to, or this every one of you can do it? How to show the whiteboard on the whole screen?
So there's something called speaker view. So I think everybody can select this, and then you.
Okay. So everyone can do it. Okay. So then I don't care about that. Okay. So what is the example? So let's take any G. Well, maybe not any. G semi-simple. Let G be semi-simple. And in the notation which I introduced, let's consider H to be equal to the semi-direct product of T and the derived subgroup of the maximal unipotent. For instance, in the SLN case, you get something like this. So you have something on the diagonal, zeros right above, and again something above, and zeros below. This is H. And also, maybe let me write G naught here and H naught here. It is not my G and H so far. And here also T naught. G is a product of G naught with another copy of the maximal torus. And H is isomorphic to H naught, but is embedded diagonally here. It is embedded as, let me write something like this, T naught prime, semi-direct with the same guy, where T naught prime is a subgroup in the maximal torus T of G, which is the double of T naught, such that consisting of elements of the form, I think, so just not to get confused, let me take a look. Yeah, so consisting of the elements of the form T square comma T. So this is the example. So H is this subgroup of G, and G is this. And in this example, we have we have 2 to the n open real Borel orbits. On which, these orbits can be parameterized by n tuples of signs. I will skip the explanation how this parameterization is defined, but the reflection. What do the reflection operators in these terms? They just switch the signs. So so n is the number of simple roots. N is the rank of G naught, and the reflection operators just switch the signs. So you see that the reflection operators in this example acts as n commuting involutions. And that's why, for instance, the braid relations of type A2 do not hold. For all other types, they do hold, but for A2, they do not hold. So our guess is that you have to somehow to extend the Weyl group, the little Weyl group, by this kind of elementary abelian to group, which gives you the action in the general case, something like this.
So that would not be a group that is acting on the torus itself anymore. Then it's more of an
it doesn't act on the torus. It doesn't act well. I mean, you may define the action artificially, but it is not the true action.
Okay. Well, thank you very much.
You're welcome.
Are there any further questions?
There is something in the chat. This is just the link to the slides. Okay.
Then let us thank the speaker again.
Thank you so much for your attention and for questions.
Thank you for coming virtually. I hope I will be glad to see you at the Weizmann Institute in person when it becomes possible.
Well, I will be lucky to get here sometime when Corona dies finally.
I will be glad to invite you when it becomes possible. I have funds.
By the way, Dima, are the borders closed? Are the Israeli borders closed for foreigners now?
Yes.
Totally.
Right now they're closed. They used to be open for a long time, maybe too long time, and too widely open, and now they are too tightly closed. We somehow go from one extreme to another in many Corona aspects.
Yeah. Okay. Well, let's hope that this complicated time will end soon.
Certainly, let's hope.
At least in Israel, there are good